Hello.
Hello, sir.
Yeah. So may I start? So am I audible properly? Oh, I'm sorry. This will be 1 minute. Yeah. Okay. So let us make a recap of the previous session. That what we have done before. That if you consider two paths, that means gamma and sigma, then so let us choose a path gamma from x0 to x1, and another one is sigma from x1 to x2. Then we have defined an operation on the path homotopy classes like this. So this is gamma star sigma. Okay. And we have already proved that this operation is, so this operation is well defined. Okay. So that has been proved yesterday. Okay. Now, whenever you are defining something, some operation, binary operations on a set, on a non-empty set, then you are always tempted to check that whether it will form some group or some algebraic structure. So here, interestingly, this happens to be true, but for some special kind of paths which are called loops. But in general, if you take any path from some point x0 to x1 and x1 to x2, and then so if you take any path from having some initial point and end point, then you will find that firstly, so let us choose a path, suppose gamma from x0 to x1. Then for that gamma, what we can have, so for this point x0, we can consider a constant path, and for this x1, you can consider another constant path, this. Okay. And while making this consideration, now you need to establish the fact that, so this will be our claim, that whenever we are starting from x0, then you will get that this will be the left identity for this path, right? Why? Because of this reason, that let us choose, so let us draw some picture here. So I am considering a path from x0 to x1, which is gamma. Now, you need to establish that there exists a map from the function h from the function that will take that identity map, that means I, there is the identity on the unit interval, closed unit interval, and another path, which is, let us call it E naught, E naught with a constant path at 0. That means it is a function from the closed unit interval to the closed unit interval, satisfying that t goes to 0. Okay. And we are taking the concatenation of this E naught star I. Okay. So these two paths, so this I and is E naught star I, so this will be path homotopic via some H. Now, if you look at the picture here, so what is your I? So what is the graph of I? So this can be, so suppose, yeah. So this is your I on 0, 1 closed interval. So this is your I. And if you want to consider this E naught star I, then what will happen? So then you need to divide the closed interval 0, 1 into two equal parts by means of the point half. So that means, so up to this one, so this is your E naught. Okay. And then you need to consider this I, which will be connecting this half with this point. Okay. So one path is along this this locus, this I, and another one is starting from here, and from 0 to half it is 0, and from half to 1 it will be this one, right? You can check. Okay. Now, since we are in a convex space, so therefore there exists a path homotopy by means of a straight line homotopy, right? So H will be a straight line homotopy between these two paths, I and E naught star I. Okay. Now you need to consider, so let me give you an exercise here, that you can prove for any two topological spaces X and Y. Okay. Suppose you consider a continuous map phi from X to Y. And now you want to consider two paths, one is gamma, another one is sigma, having the same initial point and end points. That means, so suppose this is your X, and let us have two paths. First one is gamma, another one is sigma, starting from here and ending at that point. So then what you will get, so assuming that gamma is path homotopic to sigma. That means you can construct a continuous map from this I cross I to X. This is capital F. Okay. Such that at the 0th level, the path is gamma. At the 1th level, the path will be sigma, right? Yeah, this one. Now you want to map these two paths to Y, okay? So that means via the map phi. So this is your Y. Then via this map phi, you will have again two paths. So first one is phi compose gamma, and this one is phi compose sigma. Okay. Then you need to prove that there must be some function from I cross I to Y, such that suppose it is H, and this H must be, what is that? This must be phi compose F, right? So that this diagram commutes. So that means this is a homotopy, path homotopy in between phi compose gamma and phi compose sigma. So that is what you need to prove. Okay. Yeah. So prove that phi compose F is a path homotopy between phi compose gamma and phi compose sigma. Okay. And after proving this, now let's come back to that case that you have already have at your hand, that a straight line homotopy between I and is E naught star I, right? So therefore, and you have a continuous map from the closed interval 0, 1 to that X, right? So therefore, so now let's come back to the previous case. So then, in view of this this above result, so then that gamma compose H must be a path homotopy in between gamma compose I and gamma compose E naught star I. Okay. Now, this gamma compose I, so this is nothing but gamma itself. And what is that? This will be nothing but, so since that from 0 to half, this E naught is 0. So that means it will go to E naught. That means the constant path at E naught, right? Ex naught, right? And after that, for that I, it will be gamma. So therefore, so this one is, so gamma is path homotopy 2. So this must be Ex naught star gamma. So that is path homotopy class of gamma is path homotopy class of Ex naught star of this. In a similar fashion, you can check that this will be the right identity, that is corresponding to the path, constant path Ex1. Okay. This can be done in a similar manner as above. Okay. Now, okay, very good. Now let's prove whether this operation is associative or not. Because without this one you cannot proceed further. But in that case, it is true. Okay. But why? So you need to take care of a little bit. You need to put some hearing here. And to prove this, consider three paths, right? One is, so you need to consider three paths. One is from x0 to x1. Another one is x1 to x2. And third one is x2 to x3, right? Correct. So this is your gamma 1. This is your gamma 2. And this is your gamma 3. Yeah. And you need to check that. So first you take the operation in between gamma 1 and gamma 2, and then gamma 3. So it should be path homotopic with, first you take the concatenation of gamma 2 and gamma 3, and then gamma 1. Okay. But these two are similar in view of path homotopy. But why? If you look at the definition of these two concatenations, you will find that this is nothing but, so here T goes to gamma 1 of, so since here you have three paths, so you need to divide the interval from 0 to 1 by 4, 1 by 4 to half, and after that half to 1, right? That means you need to consider for that one, you need to divide the interval into two parts, 0 to half and half to 1. And for making use of this, you need to consider again a division into equal parts of 0 to half interval, right? So therefore, so this is from 1 by 4. This is gamma 2, 4t minus 1, 1 by 4 less or equal to t less or equal to half. And this is 2t minus 1, this one. Now let's do it for this path. So this will be, so first of all, you need to consider this gamma 1 and this one together. So you need to divide the interval into 0 to half. And for that 0 to half, you will consider it, this t will be mapped to gamma 1 to t, right? And for the second part, you need to divide that interval again into two equal parts. So it will give you gamma 2, 4t minus 2, 3 by 4. And this is gamma 3, 4t minus 3, 3 by 4 to 1. Okay. So let us make a diagram here, and you will find that so first of all, consider this path. So firstly, it will occupy the bottom side, right? So 0, 1, let us make it 0, 1. So this is your 1 by 4. This is half. and then, so this part will be occupied by gamma 1, this part will be occupied by gamma 2, and this part will be occupied by gamma 3. Okay. Again, just come to the top one. Then the first one will be at from 0 to half. So it is your, so it will be occupied by gamma 1 solely, right? And then you are making a partition here into two equal parts. So this is your 3 by 4. So this part will be occupied by gamma 2, and this part will be occupied by gamma 3. Okay. Great. So you need to make some changes here. That means you need to put that 0 to half portion to this 0 to 1 by 4, right? That means you need to consider a map which will take this 0 comma half interval, close interval, to 0 to 1 by 4 interval. That means, let me, this one. And then you need to consider a map where this half to 3 by 4 will be mapped to 1 by 4 to half, right? And again, this 3 by 4 to 1 can be mapped to half to 1. And there exists such maps. The first one will be, so let me just, so for the first one, so t goes to half of t. For the second one, t goes to t minus 1 by 4. And for the third one, this will be 2t minus 1. And just by using testing lemma, you are going to have a single map. Let us call it K. Okay. So K will map this 0 half portion to 0 to 1 by 4. K will map this half to 3 by 4 portion to 1 by 4 to half, and 3 by 4 to 1 portion to this one. Okay. Yeah. Great. Now using this map, so this is nothing but this K is what? K is a map from, someone is asking that, is there a reason why we don't divide? In which case you are asking this?
Um, can you hear me?
Yes.
Yeah, okay. I was asking in this case, so like we're dividing the unit interval into like
Yeah.
half and like quarter, quarter, half, and then half, quarter, quarter. Why is there a reason why we're not just dividing it into like 1/3 and then setting gamma 1 for one of the thirds? Like,
Yeah. What I think that for convenience we are using this, I think. Yeah. Because if you
okay,
you can always have a map from any closed interval AB to CD, right? So there is
Mhm.
always a map. So you can use that, but for convenience, you need to consider this one.
Okay, okay.
Yeah. Yeah.
Thank you.
Yeah. Okay. Fine. So using this one, actually, so let me just give you an exercise. So yeah, that's a very good question. So you are going to always have a unique map. Okay. So suppose let's call it psi from any closed interval AB to CD. Okay. And you can find out the formula of this map easily, right? So that's a question exercise. Okay. Yeah. Great. Fine. So using this K, so this is nothing but this is a map from closed interval 0, 1 to closed interval 0, 1. That means it is a continuous map. So that means it is a path. It is a path connecting 0 to 1, right? And another path can be considered as the identity on 0, 1. So it is again a path from 0 to 1. So you are having two paths. One is K, another one is I, right? And since that I is a very nice kind of space, that is a convex space, so you can always have straight line homotopy there. So you can use this to make these two paths path homotopic, right? So by some straight line homotopy. Great. And then what you can do here, so therefore, so just by using the previous exercise in the last case that I've given, so gamma 1 star gamma 2 star gamma 3, and let's call this homotopy as H. So this compose H, so this must be a path homotopy between gamma 1 star gamma 2 star gamma 3 compose K. Just look at here. So this is, so here K and I are path homotopic, and you are having some continuous map from closed interval 0, 1 to X. So then you can make use of that exercise. So this is a path homotopy in between this path and this one. Okay. Now you need to compute this one. This part is obviously gamma 1 star gamma 2 and then star gamma 3. So this is obviously this one. Okay. But by definition, so what is that? Compose K. Now look at this function K. So it is sending that 0 half part to 0, 1 by 4. So along this map, so you can change the parameter to get. So this is nothing but gamma 1, right? Just look at this structure, this diagram. So this has been occupied by gamma 1, this has been occupied by gamma 2, this has been by gamma 3. So that means this is, so this will be mapped to the top side, that is gamma 1 star bracket gamma 2 star gamma 3, right? Yeah. You can check by definition also. This is a very obvious kind of thing. So that is why I'm not going to check. Okay. This is obvious. Just using the definition of this one and compose it with K. I have already given that formula. So you can get this path. So therefore, this operation is associative. Great. Now, fact 3, after doing this, you can always, so for any path, suppose you take a space here, X, so you are taking a path gamma from X0 to X1. Okay. And after considering this gamma, you can always have a path from x1 to x naught just by changing the orientation, right? So that means it can be written as, so t goes to 1 minus t. So it will be a path from t and then gamma of this, right? So therefore, this is a path from x1 to x naught. You are just changing the orientation here. So I can, yeah, this is your gamma path. Okay. So, therefore, now you want to take the operation gamma star gamma bar. Okay. That means you are starting from x naught to x1 and then from x1 to coming back to x naught. Okay. So this path will be homotopic to the constant path at x naught. Okay. Why? Because of this reason. So again, use this fact that you are considering two paths from, so one is constant path at 0. That means the graph is this one. Okay. And another one is you are taking the identity map and this I from 0, 1 to 0, 1. And again, using that function, you can define this I bar from 0, 1 to 0, 1, right? Now you want to take the concatenation of this I with I bar. So that means this will be, so the graph will be something like this, and this. Okay. So this is your I. So you are going to 0 to half and then half to 1, it is I bar. Okay. So you are having two paths. One is E naught and another one is I star I bar, right? So again, you are using the convexity to have that these two paths are path homotopy, right? And therefore, this will imply that, so you have this gamma, so this gamma compose E naught will be path homotopy to gamma compose I star I bar. And this part is obviously, this is x naught, ex naught, and this part is obviously gamma star gamma bar, right? So therefore, this holds good. In a similar way, just taking the operation with the path homotopy class of gamma bar with the path homotopy class of gamma, then this will be ex1, right? So these are, so with respect to that ex naught, the class of ex naught and ex1, we are having the left inverse and right inverse, right? So therefore, what will make so how to form a groove? So we are taking the paths by collapsing the end point, the terminal points, right? That means we need to take, so we need to take some, so that means some loop starting at x naught ending at x naught. So we are collapsing the terminal points to make a loop, right? So we take loops at x naught. That means there is a path in x that begins and ends at the same point. Okay. Now consider a point. So let us call it x naught. So best at x naught, if you consider a point in the space x naught, you can always think of a set. Let us denote it by pi1 x x naught, and it is the set of all path homotopy classes of loops based at x naught. Okay, and this is a non-empty set. So this set forms a group. With respect to the concatenation of paths or path homotopy classes, right? With respect to the concatenation of paths of path homotopy classes. Okay, this group is called is known as the fundamental group of x based at x naught, and sometimes it is called the first homotopy group of x. Okay, just look at this example that we have already seen that the Rn is contractible, right? So look at the n-dimensional Euclidean space. Suppose you take any point x naught and taking any path, any loops, right? So any loop, so suppose this is your gamma, then this gamma can be deformed to that x naught continuously due to convexity by straight line homotopy, right? Yeah. So this gamma can be deformed to the constant path ex naught due to the presence of convexity in Rn, right? So that means whatever loop you are taking based at x naught, this will be deformed to the constant path ex naught, right? So that means the fundamental group of this Rn will be the trivial group, right? Great. So this Rn will have a trivial fundamental group. Not only Rn, we have already seen that Dn was a contractible space, right? So it is interesting to be noted that the fundamental group of the closed unit sphere based at some point x naught must be a trivial group, right? Not only that, if you take any convex subspace in Rn, then with respect to some point on that space, the fundamental group will be a trivial group. Okay, so pi a some Cx naught, where C is a convex subspace of Rn, so will be a trivial group for any convex subset C in Rn. Okay. Okay, great. So as of now, so the fundamental groups of some familiar spaces turns out to be a trivial group. Okay. But if you are not getting any fundamental group which some space which will be a non-trivial group, then there is no possibility of discussion on these fundamental groups, right? So our goal is to find out the space having non-trivial fundamental group. Okay. So before coming to this, we need to put some care on that base point, right? Whatever we have defined, maybe sometimes one might be confused that whether it depends on this x naught or not, right? If you are changing this x naught, whether the group will change or not. Okay. That means suppose you take some space. So let us take one x naught and another point which is x1. Okay. So does there exist any connection between the fundamental group based at x naught and the fundamental group based at x1? Okay. That means if you are considering loops around x naught, and if you are considering loops around x1, whether these loops are connected or not. Now there is a possibility if you can find out a path between these 2 points. Let us call it alpha. Then using this alpha, you can define an association in between a loop based at x naught and a loop based at x1 by okay, so let me just do it. So let gamma be a loop at x naught. Okay. Then so I'm just taking this is gamma. Okay. And this is your alpha. X naught and x1 are connecting by this path. Okay. And since gamma is a loop, so you are starting from, so starts at x naught, then coming back to x naught again via gamma, and then going around this locus of alpha to x1. Okay. And then come back to okay, I'm sorry, we need to start, I'm sorry, yeah, starts at x1. Yeah. So by this path, which is the inverse of alpha, right? To x naught via alpha bar, and then going around this gamma via gamma, and after that coming back to x1 again via alpha. So what does it say? So that means your you are defining some loop based at x1. What is that? So corresponding to this gamma, you are considering this loop, right? So this is a loop at x naught, and this will be a loop at x1. So therefore, we are making some association in between the loops based at x naught and the loops based at x1. That means, so this gives you a map. Let us denote it by alpha cap, because it depends on alpha, right? So that is why we are denoting it by alpha cap, which is from pi1 x comma x naught to pi1 x comma x1, and the map is given by this rule. So alpha cap. So this is the first one is alpha bar, then gamma, then alpha. Okay, this is true. And few facts can be checked. First one is this map is well defined. Okay, this is true. Secondly, this is a, so since this is a map between two groups, and this is a well defined map, so therefore we can check that whether it is a homomorphism or not. So certainly it is a homomorphism. Okay, just using two paths. One is the class of gamma, and another one is class of sigma, and then take the composition, then the concatenation there, and you know that this alpha star alpha bar is always homotopic to ex naught, right? And you are using this fact to get that this is a homomorphism. Okay. So this is a homomorphism, and by definition, this is on 2, right? What you do, suppose you take some path, take some loop around based at x1. Okay, and then so let us start from x naught to x1 via alpha, then going around this sigma, and then coming back to this x naught via alpha bar. Okay, so corresponding to this loop sigma based at x naught, you can consider a loop based at based at x1. You can consider a loop based at x naught, which is this. So this is a loop based at x naught, and you can check that this loop will be mapped to class sigma, just using this fact, this one, and the reverse one, this. Okay, great. Yeah, I think this one. Yeah. So therefore, this is on good. Okay, and also this must be 1 1. Why it is so? Because if you take that corresponding to the gamma, corresponding to this path gamma, this loop, So this equals with this one. What does it mean? That means these two paths are path homotopy. Alpha bar star gamma star alpha is path homotopy to x naught. Okay. So what does it say? So this one is nothing but alpha star ex naught star alpha bar, right? You're just multiplying the classes, class alpha from left, class alpha bar from right. Okay. And this is nothing but this one. Just using this. Okay. So therefore, this function is 1, 1, on 2 and a homomorphism. So therefore, so if there is a path from x1, x0 to x1, then interestingly, the groups are isomorphic. Okay. Great. So that means if you are considering a space, so if X be a space and if C be a path component of X containing a base point, let us call it X naught, then you see that the fundamental group of X based at X naught is nothing but it is isomorphic with this, right? So it will not change on the path component spaces containing that base points, right? So that means this depends on the path components of X containing that base point. Okay. So if you are looking at a path connected space, is a path connected space, then the groups are isomorphic. Whatever base point you choose, these are all isomorphic. Okay. Now one will see that the groups are isomorphic, so we have done, right? But there is a very delicate thing that is happening here. So if you look at the loops, suppose you look at the loops at x naught and the loops at x1, so there is no natural way to identify the groups, fundamental group of X based at X naught and fundamental group of X based at X1. And if you take a close look on that, let us make it another remark that if you choose two paths, okay, suppose this is your alpha and let another one is beta. Okay. If there is two paths from x0 to x1, then for that alpha you will get alpha cap, and for that beta you will get beta cap, right? Now if it is happening there that if alpha is path homotopic to beta without changing the terminal points during the homotopy, then these two maps are same, right? But if it is not, then what will happen? Okay. So that means, so omitting the base point, will uh, yeah. So omitting the base point will give us a delicate a confusion, right? So what is happening here? So now just look at this case. Now suppose you take this alpha. Suppose you just start from x naught via beta and come to x1, and then coming back to this x naught via alpha bar. Okay, that means we are considering. So we consider the loop beta star alpha bar, right? So this is a loop based at x naught. Okay. Now for any path homotopy class of the loop gamma based at x naught, we see that. So we have a specified loop here based at x naught. So given any loop based at x naught, what is happening? Now, if you just take that assumption that this homotopy class will commute with this homotopy class of gamma, then what is happening here? What is the case? So this implies, so certainly just you need to execute some computations here to get. So it is beta alpha bar star gamma, and it is gamma beta alpha bar, right? And then, okay, no, I'm sorry. Yeah, beta alpha bar star gamma, and this is gamma star beta star alpha bar. Okay, so multiplying both sides by the class of beta bar from left and the path homotopy class of alpha from right. So then you will get, so this is and sorry, star alpha, yeah, and this is alpha beta bar star comma star beta star alpha bar star alpha, right? Yeah, great. So this implies, so this one, this is nothing but the identity at x1, that means class ex1, and this one is again the identity at x1, that is class ex1. So that means you have, so this is alpha bar star gamma star alpha, and this is beta bar star gamma star beta. So what does it say? So it says that the functional values at class gamma are same. They coincide, right? So alpha cap equals with beta cap. Without knowing that whether alpha and beta are path homotopy or not, I can have this possibility. Okay. So that means this shows that the map alpha cap will be independent of the choice of paths if and only if for any beta, for any path beta from x1, x0 to x1, the loop beta star alpha bar based at x0. So its corresponding class will be in the center of that group, right? And this suggests us to make a remark here. So certainly this is independent of paths if and only if this is abelian, right? Good. But still, since we have making use of that alpha cap, which is an isomorphism in between two groups, fundamental groups based at 2 points x0 and x1, which are connected by a path. So whenever we are considering, we are talking about the properties of groups, then we feel that in a path connected space, these are all isomorphic, right? Great. Now let us define a very nice kind of spaces that has been studied in complex analysis, which are simply connected domains. So let me call it simply connected space. So a space X is defined to be simply connected if it should be a path connected space, because without having this, you cannot say that the fundamental group is trivial for all the cases, right? So if X is path connected, and the fundamental group with respect to some base point x0 is the trivial group, right? Okay, so with respect to this definition, you have already at your hand some examples of simply connected spaces, which are Rn, Dn, and any convex subspace of Rn. Okay, so that means, so examples are Rn, Dn. So these are all simply connected. Okay, but we have seen some space. What is that? So what would be the case for the punctured plane? Okay, is it simply connected or not? Okay, so let me just have a very nice observation that if you are dwelling in some simply connected space, then any two paths having same terminal points must be path homotopic. Okay, so that means, so suppose you take any path here, so these two paths are path homotopic in a simply connected space. Why? Because suppose, what is the reason? So suppose gamma and sigma be two paths in a simply connected space. So assume that xp simply connected, and you are choosing two paths having same terminal points. So this is a path from x0 to x1. So suppose this is your x0 and this is your x1. Okay, Now, with respect to these two paths, you can always define a loop based at x naught. What is that? That starting from x naught via this sigma, okay, and then coming back to this x naught again via gamma bar. So you will get a loop based at x naught. So therefore, the sigma star gamma bar. So this is a loop based at x naught. But since you are living in a simply connected space, so the path homotopy class of this loop turns out to be the identity, trivial element, right? And therefore, these two classes are same. That is, sigma is path homotopy to gamma. So any two paths having same terminal points are path homotopy. And in view of this, if you consider let us have a look at the punctured plane. So suppose you are taking out this 0, 0 from the plane, and now you consider the circle, semicircle here. Okay, so this is suppose gamma, which is given by t goes to cos of t sine of t, and another path can be given by having the same terminal points, this one, which is again a part of a semicircle, part of the unit circle or the lower half plane. So this is sigma, which is t goes to this one. Okay. Now these two paths, now one cannot deform gamma to sigma without crossing 0, 0, right? Continuously. So that means this gamma will not be path homotopy to sigma here. So certainly, in view of this proves that this is not simply connected, right? Although it is path connected, but it is not simply connected. So in view of, so with respect to this space, so that means the fundamental group of this space will not be a trivial group, right? So this implies this is not a trivial group, right? We can characterize this group later using covering spaces. Okay. And before going to this notion, we need to establish another one, that if you are looking at two spaces, suppose x and y, you need to consider some association between the fundamental groups of the spaces x and y with respect to the base points x naught and y naught, assuming that x naught will be mapped to y naught via the continuous map h. Okay, so that means, so now let h be a continuous map from x to y, supposing that we are choosing some base point here in x and y naught, and they are connected by this h. So hx naught must be y naught. So we need to set up a map from the fundamental group of x based at x naught and the fundamental group of y based at y naught, right? So we can denote this function like this. So this is a function from x naught to y naught. Okay, displaying the assumption that hx naught is y naught. Okay. So what would be the map? So that means, suppose you have this x and you are considering this x naught the base point. Suppose this is a loop here. Let us call it gamma, and then you are going to move towards y via this h. This is y naught. So that means this h will give you some association between these two loops. One is gamma, and another one is, if you are composing this gamma with h, then it will be a loop based at y naught. So that means it is h composed gamma, right? So therefore, this defines a map. Let us define it in this way: h star, or let us hx naught star. Okay, so this is a map from the fundamental group of x based at x naught to the fundamental group of x, from fundamental group of y based at y naught by the rule. So hx naught star of gamma goes to the class of h compose gamma. Okay. Now, one might be confused that whether it is well defined or not. Certainly, it is well defined because of that exercise. Okay. So suppose you take two paths. One is gamma, another one is gamma dashed. And if they are path homotopic in x, so these are loops based at x naught, and these are path homotopic in x, then you must have some path homotopy in between, which are connecting this, which are deforming this gamma to gamma dashed continuously. So via a path homotopy f. Okay, and then this path homotopy will give you the path homotopy which is h compose f, right? And this will be a path homotopy in between these two paths. What are those? So h compose gamma and h compose gamma dashed. Okay, so therefore this implies the classes are same, and this implies that x naught star is well defined. Okay. Not only that, it is very much easy to check that this is not a, this is a homomorphism. I'm just leaving it to you to check. Okay, check. Great. Now, with respect to this homomorphism, so that means this is a homomorphism from the fundamental group of X based at X naught and fundamental group of Y based at Y naught. Okay. So if you are assuming that, if you are considering three spaces, one is X, and if you consider a continuous map here, let us call it H. So X naught, Y naught, and another map from the space, let us call it K, Y naught to Z naught, right? Then you can at once prove that, so these two continuous maps will give rise to two homomorphisms on the respective fundamental groups. That is, one is H X naught star. So this is a homomorphism in between these two fundamental groups. And another one is K Y naught star, which is again a homomorphism in between these two groups. Okay. And therefore, so if you are composing these two maps, H and K, then you are having a continuous map in between X naught to Z naught. And this will give rise to another homomorphism, which is K compose H X naught star from X naught to the fundamental group of Z based at Z naught. Okay. And it is easy to check that this K compose H star is nothing but this K star compose H star. Okay. And with respect to this and the identity map on the space X, so that identity map will give you a homomorphism between the fundamental group of X to itself. So therefore, if H happens to be a homeomorphism, having satisfied that Hx naught is Y naught, be a homeomorphism, then what will happen? Since it is a homeomorphism, then you are having a continuous inverse, which is K, which is from Y naught to X naught, right? So H and K are two continuous maps. So H is from X to Y and K is from Y to X. Then this H and K will give you two homomorphisms. One is from the, so H star from this one to pi 1 y naught, and K star is from pi 1 y naught to pi 1 x naught. And therefore, in view of the above result, so this K star compose H star, what is that? So this is nothing but K compose H star. But what is K compose H? This is the identity, right? So therefore, this will be, so this will be the identity on this one, on the fundamental group of X based at X naught. Similarly, this will be the identity on the fundamental group of y based at y naught. Okay, and so this proves that. So therefore, what does it say? These are isomorphic. Okay, so that means if two spaces are homeomorphic, and if you choose any, suppose you are having some path connected spaces, you're considering x and y to be path connected, and if you choose base points, suppose x naught, so this will be mapped to the image of that map, suppose it is y naught, then the fundamental groups are isomorphic with respect to that base point, right? This is a very nice observation. Okay, so if two spaces are homeomorphic, then the fundamental groups are isomorphic. Okay, great. And okay, so certainly from this one, you can say that if you are having two spaces, suppose one is two fundamental groups which are non-isomorphic, right? Then you can say that the spaces are not homeomorphic. Okay, so this is a very nice result. Okay, and it is true. So for example, you can check that this is a space having non-trivial fundamental group, right? But still, so still it is simply connected. So that means this space will be having trivial fundamental group, but it will be having non-trivial fundamental group, right? So in view of this, you can say that R2 and R3 are not homeomorphic, right? So therefore, R2 and R3 will not be homeomorphic. Great. Now again, okay. Good. So now let us introduce the covering maps. I think I can spend 5 minutes more. So let me just explore a very nice example before going to the definition of what does mean by a covering map or covering space. So let us have a look at the following example. Okay. Suppose you are considering the unit circle. Okay. So this is S1. And we know that there is a continuous surjection. So let us call it P from the real line to S1. By means of this map, P of t e to the power 2 pi I t. And certainly this is a group homomorphism and it is also a continuous surjection, right? Okay. Now let us take, so this S1 will be assumed to be equipped with the usual topology, right? That means a topology that has been induced from R2. Okay. And with respect to that, you can take an open set in S1, which is suppose this one for the right half plane, this one, okay? Suppose it is U, okay? That means what is U? U can be written down in this way, that this is nothing but the set of all those points in S1 having positive first coordinate, right? So that means in terms of the cosine and sine functions, so this is cos 2 pi t, sine 2 pi t, where this is greater than 0 for all t, I'm sorry, for all t belongs to R. Great. So this is an open set in S1. Okay. Now, what would be the inverse image of? So, what is P inverse of U? Well, just look at this open set, and if you are considering the arguments of that complex numbers, so that will be running from minus pi by 2 to pi by 2, right? So therefore, this 2 pi t is this, right? So that is, what does it say? So that means it is 1 by 4 to 1 by minus 1 by 4 to 1 by 4, right? And since you are getting every time, if you are rounding around this S1, you are getting this kind of region. So you can take, so this implies that P inverse U will be union of n minus 1 by 4 to n plus 1 by 4, right? So that means, suppose you are taking this, so for that open set U, this is your map P, this is from R to S1, okay? So this will be mapped to minus 1 by 4, 1 by 4, and then it is 3 by 4 to 5 by 4, and so on, right? Yeah. So each of these small particular intervals, open intervals, will be collapsed down to U. Why? Because of this reason that, so let Vn is the closed interval, n minus, the open interval, n minus 1 by 4, n plus 1 by 4. You just take any one of this, suppose this one, okay? Now, note that the map T goes to this map, this coordinate map. This is certainly strictly increasing, okay? So this is strictly increasing, and which means that the map given by P will be 1 1 from, so this is a continuous map from Vn. So let us take the closure of that. to u bar. Okay, just including the endpoints. Okay, so this is a 1-1 map. This is onto. Am I correct? This is onto. This is a continuous map, and therefore, why it is onto? Because of intermediate value property, right? So by IVP, you can check. And this is a compact space. This is always a T2 space, right? So therefore, this is a bijection from a compact space to a T2 space. What does it say? This implies that this map should be a homeomorphism, right? From Vn bar onto U bar, particularly P will be a homeomorphism from Vn to U, right? This is a homeomorphism, right? That means these intervals are all homeomorphic to U via P. So what does it say? That means you are just taking these intervals and these are accumulating towards 1, and then it will be crashed down to this U. Okay. So that means one can say that these are all a copy of U in the real line via this P, right? And not only that, this P inverse U is the union of these open intervals. Okay. So we are saying that this kind of U is called, so it is defined to be evenly covered by P. So generally speaking, what is happening for a general map from a so suppose you take a continuous surjection. So suppose P be a map from some space E to B, which is a continuous surjection. Okay. And if it happens to be true that suppose you take take the space. So this is P, this is B, and suppose you're having some space here. This is your E, this is P, and this is your U. And if it is true that the P inverse U will be looking like this. And so on. Okay. Yeah. That means you are having some copy of U via this P inverse, right? And these copies are crashed down to this U. Okay. That means if you take any, so these are called slices. So if you take any slice, let us call it V alpha. So this map will be homeomorphic to U via this P. That is, V alphas are homeomorphic with U. And if it is true, then U is called. So that means, let me write down the formal definition. So U is called is defined to be evenly covered by P if P inverse U can be expressed as a union of disjoint open sets. Okay, disjoint union of open sets V alphas in E, okay, such that if you take the restriction for each V alpha to U, so that is going to be a homeomorphism. So if it is true, then that neighborhood U will be called evenly covered by P. And the collection, so the collection of open sets V alpha is called a partition of P inverse U. Okay? And V alphas are called slices. Okay? Now, if you look at the example, this one, this U is evenly covered by P. Not only that, if you take any open set, suppose this S1 being a compact set, so you can represent it as a union of finitely many open sets. So let me just do it. So one is, suppose let us call it U1. This is U1. Okay. This might be U2. This will be U3, and this one U4. Okay. So this S1 can be written as U1, U2, U3, U4, right? And after that, if you take any point in S1, so it will lie either in U1 or in U2 or in U3 or in U4, right? So that means around any point, you are getting a neighborhood of that point within that S1, which is evenly covered by that map P, right? So this kind of situation can be handled in this way. So you can define that. So if for any point, so for any point, so if for any B belongs to capital B, there is a neighborhood U of P in B such that U is evenly covered by P. Okay. Then the map P is called a covering map. And E is called a covering space of B. And through this example, we have already seen that R is a covering space of S1 with respect to that covering map P. Okay. So with this one, I would like to stop. Any question? If there is no question, then we may leave, right? And we will meet again tomorrow at the same time. Okay. Yeah, Luisa, yeah. Thanks to all of you for listening me. Okay.